vedere tutti sì, comunque va bene. Sì.
Okay. Good afternoon, everybody. It is a pleasure to see you today, and I wish to thank the committee for their attention and for their care. My thesis is real-time exercise recognition and repetition counting for monocular gym video. I did it with many thanks from Professor Stefano Matoccia, my supervisor, and my co-supervisor, Enrico Manocci. A little bit of background. Gym machines today are capable of tracking exercises automatically. That means they are capable of knowing the user, knowing the repetitions, and the weight and the exercise. However, there does not exist any exercise tracking solution for free movement exercises. Also, wearables are not a solution in commercial gyms because they are independent products that cannot be shared between users for hygienic reasons, and there faces some opposition from users to wearing wearables at all. Therefore, Sauna Health and Fitness, a gym here in Bologna, offered me the proposition to solve this research question. Are we able to repurpose their existing security camera system, which you can see on the right here, as a high definition feed with a wide angle of view and with many different camera perspectives, to identify exercise types and count repetitions in real time? My objective is to develop a system that, utilizing a single monocular RGB camera, no depth information, is capable of identifying the exercise type. As you can see, the lady on the right has been identified as performing a lateral raise, as well as counting the repetitions, 10, in real time. To achieve this, we need to run at a under 100 millisecond budget for the processing of the entire pipeline. We need to work with variable camera angles, as well as with a 2D projection that loses accuracy in the angle values. You can see the lady on the right, even though her shoulders are at the same height, the system has counted 95 degrees and 65 degrees respectively, and we need the class agnostic repetition counting. To do so, we will use this system architecture. The camera is capable of outputting at 4K 10 FPS. We sample these video frames down to 1080p and pass them through a media pipe glaze post position estimator. This provides the skeleton on the woman. It also provides the blue bounding box. This pose estimation that contains 33 key points are extracted into 14 angles, which I use expert assistants to decide as the most salient, and 14 associated visibility scores. So whether the shoulder, for example, is occluded or not. Then, this is passed onto a temporal convolutional network that uses the sequence of the 28-dimensional vector to calculate the exercise label. In parallel, that blue bounding box accumulates frames of the user performing their exercise. These frames, once the exercise is finished, the entire sequence is passed to a repetition counter called RepNet that counts, and both the label of the exercise and the count are uploaded to a database and displayed on a front end in real time. To do so, I had to create a data set. This data set contains 16 classes, one of which is the other to solve the open world problem, and 15 exercises chosen as the most useful by the experts in the gym that users typically do. We use augmentations to increase the dataset size to 959 videos, extracted at 10 frames per second, along a video level split of train, validation, and test. That is a little different from the typical splits, but that's because it follows the video files, and we didn't want to bleed any known videos into the test set. This totals 500,000 frames, and it is publicly available on Zenodo for others to continue the research. The classifier is a temporal convolutional network. We chose this because it offers parallel training and simpler architecture than the LSTM. we stacked 3 dilation blocks with 1, 2, 3, so that to achieve an effective receptive field of 29 frames. You will notice this is not the 60 time steps that it takes over an entire frame window, so we utilize global average pooling to accumulate an entire representation of the exercise. And why 60 frames? Because at 10 FPS, that's 6 seconds, and even the slow exercises have 1 repetition completed within 6 seconds. Then this is passed to a softmax to produce the 16 classes. In parallel, we need to count the exercise repetitions. To do so, we utilize the model RepNet, which is completely exercise agnostic because it generalizes via periodicity in a sequence of images. This user performing sit-ups will perform 10 of them in the video, and the cropped frame buffer is fed into RepNet to build a self-similarity matrix, which you can see on the right. There is one big bright yellow diagonal, that's the similarity of the frame to itself, but to the left and right of it, you will see other diagonal stripes. And if you count from left to right, there are indeed 10 of them. This worked very well, with only one limitation, that isometric exercises, where no movement is required to get the exercise done, cannot have a periodicity. So for these, our results are in time under tension, which is the number of seconds that the exercise was performed. Here are our end-to-end test results. This means the generalizing of our entire pipeline to real gym video, including complete workouts. And going along the combined scores, there are a total of 61 sets that were registered, where 83.6 of them were detected by the classifier. That means it found the exercise. 92.2% of them were correctly classified, so it labeled it as it should. And in parallel, we have a mean absolute error of 2 for the repetition counter. So given 10 repetitions in the ground truth, between 8 to 12 were recorded, with a plus or minus 3 tolerance given by the experts as an acceptable tolerance of 91% score. This is lower than the on-test classification performance of just the TCN, which was at 96%, where 7 classes achieved perfect precision. Notice that I have excluded Workout 2 360, and it has lower results. Why could this be? Workout 2 360 belongs to another test that we ran, where we took the same exercise workout from the security camera perspective, which is the elevated 3/4 perspective, and from the users putting up a camera perspective, which is the level frontal perspective. And we observed that the classifier, the TCN, had a sharp drop of 33 percentage points in detection. Why could this be? This stems from the 2-dimensional projection that we used earlier to calculate the angle values. So geometrically, the angles are distorted, and therefore, in the training data of the TCN, it was not able to generalize to a different distortion. Even though we used augmentations, we used temporal augmentations to speed up or slow down the video, we used flip augmentations, but they could not solve this problem. The solution, well, to talk more about the problem, the reason is that this is exactly the formula that we use to compute the angles, and you will notice that we use the pixel positions, which because of perspective projection, each joint has a different depth. And therefore, when we use only the X and the Y pixels, depending on the perspective, the angle will appear different in reality. Here is an example for the audience where at the top, you can imagine you are looking at the slide, and from the side, it would be the camera is here. And the arm has appeared to be foreshortened. The solution is to recover the depth, so to add in a monocular depth network. This will allow us to calculate viewpoint invariant 3D angles and is a future work. In summary, the project is a success. The gym, Sauna Health and Fitness, is very pleased with the results. and they have contacted Technogym from Cesena, which is a worldwide famous producer of gym equipment, and we will be providing a product demo for them in April. While end-to-end models dominate current research, we are happy to show that a modular pipeline is still a great solution for this problem, and it is capable of doing it in 82 milliseconds per frame on just a laptop, an Apple M1 to be specific, with the possibility to expand the network. We also showed that 28 features is all that is necessary for the temporal convolutional network. So this shows that this network architecture is well positioned for this particular problem, and that the RepNet was able to generalize very well, with a 91% of its repetition counts falling within +3, with no fine-tuning. The dual camera study highlights the perspective change problem that is yet to be solved, and that is our primary future work to add this monocular depth integration, which my Professor Matocha has a very exciting, lightweight monocular depth network right now getting published. So I can't talk about it, but this exists in 2026. And finally, we are happy to share the data set on the internet, on Zenodo, for anyone who wishes to continue this research, as well as verify the results. I thank you very much for your time today. It has been a pleasure presenting. Are there any questions?
So, first of all, very well presented. If you had to identify any bottleneck in the pipeline, I mean, the area where the most improvements could be done, what would that be? Obviously, you mentioned already one. I mean, camera placement plays a big role, and if you can estimate depth, you can get a better, more realistic representation of the angles. Are there other areas which you think could be improved?
Absolutely. The bottleneck that bothers myself personally the most is the pose estimator. Okay. Because while it's open source and therefore I could use it with a commercial license without the company paying any fees, it is quite old now. Okay. It's from 2020, and therefore it doesn't work for parallel detections. So this system, which is coded to work on multiple users at a time, right now is bottlenecked by its pose estimator. Exactly.
Which is a single user, got it.
Exactly.
Okay, thanks.
Thank you very much.